Hello, and thank you for inviting me. Can I see who attended the machine learning workshop yesterday? Machine learning workshop? Oh, okay. Some people. All right, so I'm going to talk kind of very basic ideas about CNNs and how you can think about deep learning from a very practical point of view. My name is Martin Andrews, as he said. I'm a Google developer expert, which means that Google pays me to fly places, but they don't pay me. So, in some sense, I'm an idiot that does machine learning. I have a logo here with a Red Dragon AI. It's a company based in Singapore. And me and my partner Sam, who gave a talk this morning, we do kind of education. We're also working on our own products. So what I want to just describe is kind of what we're trying to do with these CNNs, what they are, and basically I'm going to do this in a code-first way, and I'll explain what that is. And then I'll talk about how to train these things. I'll train a model to do the standard thing, something a bit different, and if there's time, I'll do something with like a pre-trained model. So let's look at the problem. What I would like to do is to take a stack of images over here, and I want to do some kind of model which will do some processing here, and at the end of the day, it will give me a probability of each class. So in this case, it's going to choose between a car, a truck, or whatever, a bicycle. And so basically, I want it to go through a series of manipulations, which will then give me a string of, like a list of probabilities. And so this is going to be my task. If I can do this well, then I get paid. Okay? So let's have a look at what CNNs are. So this is kind of the standard way. Convolutional networks, what you do is you know that you need a translational invariance, and you have derivatives, but I'm not going to do that today. The standard way of doing this is to explain the neurons in the brain and build slowly up. I'm going to go straight into the code thing so you can see how it actually works. Code. So I'm also going to do something which people say never to do, which is to do pure live demo. So here we go. Oh, come on. This is why they say never do it, right? There are various Wi-Fi issues here, is the problem. Sorry. Sorry, here we go. Sorry, just a minute. I'm going to hotspot in just because I have to. So what we've got here, who here has seen Google Colab? Lots? Many? Who here has used Jupyter Notebooks? More, okay. So the key thing about the Google Colab is you basically get a Jupyter Notebook for free running on a free virtual machine in the cloud. So you can see here that this virtual machine has got a decent amount of RAM, decent amount of disk, and if I go into the runtime, I can see I've got a GPU. So Google has allocated a GPU, a T4 GPU, which is kind of like a 1080 NVIDIA card, which is quite a decent thing. So right now, I'm not going to buy an NVIDIA card. I can run this for free in the cloud. It gives you 12 hours at a time, and after 12 hours, you can restart it. So as long as you have a kind of a scheme for saving your data and reloading back your checkpoints every 12 hours, you can train models full-time, every day, forever on Google things. So that's kind of a nice thing. So what I'm going to do here is, because it says TensorFlow 2 on the label, I'm going to install TensorFlow nightly. So TensorFlow itself, which comes with the Colab, is at 1.13 or 1.14. So this is kind of the very last of the 1 series. But TensorFlow 2 is the new hot thing. Basically, you can think of it as TensorFlow, but PyTorch. So what has happened is, since the beginnings of TensorFlow, which is very much a kind of a graph-based analysis package, PyTorch has come along. And PyTorch is super easy to use and is very attractive as a researcher to use this to program in. And this is something which Google is very nervous about, we understand, and realize that people want the ease of use of something like a PyTorch, as well as the advantages that having a full tree or a full graph gives you. So I won't go into exactly what those advantages are, but basically I'm going to install this. I'll import TensorFlow. And the nice thing about TensorFlow is this is what's called eager mode, which is TensorFlow is now eager by default, is basically if I take a TensorFlow constant like this matrix and just multiply it by a number, I now get the result back immediately. So this is something which TensorFlow before would not have done for you, and that TensorFlow before would have taken that constant, and only when you ask it to evaluate a graph in a session would have given you the result. Now you can get the results instantly, which is much nicer to work with. So here what I can do is I'm going to make this into an image. So this is basically taking the matrix I just made, making it into float 32s. I'm now going to expand the dimensions. So you can think of the image I got as just a 2 by 2 array. And for various kind of technical reasons to do with how CNNs work, I'm going to want to add a color column. So this is a monochrome image, but it's always going to want to have this as a one-channel image. The other thing is that these things, because it's like a GPU or a TPU, wants to do these things in big batches of data, which is where they really become efficient. I will also add another dimension at the beginning, which to say I have a batch of one single image. So this is kind of a technical thing which I have to do to make all the nice Keras functions work. So I will also then do a little color map with some matplotlib, and this is showing what the contents of the matrix is. Okay, so it's an image. It should be nice to look at. So there's a happy image for us. So what we're going to do with the convolutional layer, and this is how convolutions work, is we'll take a tiny little matrix here, this kernel, which is a 3 by 3 kernel, and we're going to move it across the image. And at every position, we're going to now sum up the contents of this, multiply it by these numbers to get these answers. So this is, if you just look at it's -1 times the 3, -1 times 3, plus 0 times a 0, plus 0 times a 1. We can just add these up. Basically, we can apply this convolutional kernel across the entire image to get out another image. So what I'm going to do now is I'm going to create this is a Keras layer called conv2d, which is going to do this operation. It's going to produce one output channel. It's got a 3 by 3 kernel. And basically, I'm going to give it this as the kernel initialized, which is a 1 in the middle with zeros around the outside. Now, what you can see here is when I apply it, basically, I'm going to get another image out. It's not obvious what it's doing there. But what I'll do is I'll make myself another little helper function, a before and after. So basically, I've got a before image, my little convolutional kernel, my after image. Now, my after image, because of the way in which I did this, basically the middle thing is just doing a copy, and the stuff around the edges are doing a 0. Okay? So basically, this is kind of the identity kernel operator. It's just scanning the same thing, and I'm getting the same thing out as I put in. But let's make it a bit more complicated. Here, I'm going to use a little kind of cross shape. So in the middle, I've got a half, and to the left and right and up and down, I've got a quarter. So if I now have a look at the before and after on that, basically, I've got my image coming in just the same as before. Here's my little cross-shaped kernel. And output is now a kind of a mixed-up version of what went in. So for the eyes on my smiley face, it's not very emphasized because there's nothing to support the middle thing. Whereas on the mouth, the actual sides of the mouth kind of support that middle pixel, and so you get like a really bright area and the stuff which has got stuff to the sides. This particular kernel doesn't like the diagonals, but it likes things which line up, right? So this is highlighting the mouth. So let's try another one. This one's kind of like a diagonal shape like this, okay? And the things which is highlighted strongly here are these corners of the mouth, basically because this kind of lines up with the kernel. Now, I've made the color map so that the black is 0, white is for 1, and red is for negative numbers. So it's kind of easy to see what's going on. Even though I've got this kind of positive and negatives here, you can see that it really doesn't like these places. It loves the corners of the mouth. Okay? So another operation which we're going to do to make up, so I'm going to basically build like a palette of different things we're going to use. So this conv2d, you can see kind of what it does, right? If I have all these kernels in the middle, I can produce different pictures, okay? Another thing I will use is a thing called ReLU. And basically, if I take what I will do is I'll take this sort of this little vector, which is 0, -2, -1, +3, +2. You can see that this is the colors according to the numbers, right? And what I can then use is a thing called this Keras framework, which has all these things built in. So before we saw conv2d, which was built into Keras. Here we've got ReLU, which is built into things. So basically, the ReLU is like a diode operation. So it'll take all the positive stuff and just pass it through. All the negative stuff, it will just set to 0. So you can see that all the stuff which is either black or red comes out black, and the other stuff is unchanged. So this is a very simple operation, but it's a non-linearity which is will come in essential. The last one I'm going to show you is softmax. Now this is kind of a more difficult operation, and hopefully you can see this, okay? Basically, I'm going to take all of the inputs coming in, which could be plus or minus numbers, and I'm going to raise them all to the power e. Now what that does, it sounds complicated, but what it does is it makes them all positive. At the very least, I know they're going to be positive numbers. If I've got e to the 1, it's kind of like e. If I've got e to the 0, it's going to be 1. If I've got e to the -1, it's going to be some nasty fraction, but it's still above 0. Okay? So this is a kind of thing which will convert any range of numbers into some nice positive numbers. And what I'm going to then do is I'm going to divide it by the sum of all of those, so that if you think about it, if I take the sum of all of these things, even though I've raised them to the power e, and I divide by that, it means the sum of my output is now going to be 1 in total. So I've got a list of numbers which are all positive or 0 and sum to 1. Now that is the same as a list of probabilities. So basically I'm going to call these probabilities as the output because they have the right kind of things to be probabilities. I've no idea whether it will generate actual probabilities, but it's kind of the right stuff. Okay? So what I can do here is if I take my original things, which is the 0, -2, -1, I can then do this softmax operation, and I can then show what it looks like. So here you can see that basically the highest one here is coming out as kind of some lighter shade of grey, and the others these are pretty much black over here. Okay? It kind of likes the peaks, doesn't like the rest. And one thing I can do, which will come in kind of handy maybe a bit later, is I can have a parameter called temperature, which is something which I can just kind of scale my softmaxes with, so that if I have a temperature of 1, it is what we started with. If I have a higher temperature, if we think to like thermodynamics, a higher temperature, it makes things kind of more equal, whereas if I have a very low temperature, it kind of solidifies on an answer. So that by varying this temperature parameter, I can choose between essentially searching and fixing on the answer. So this is a kind of explore and exploit idea. So just by changing this one number, I can use softmax to actually do a variety of interesting behaviors. Anyway, so let's go back to this. So we've got the layers now. So we've got the conv2d, the ReLU, and the softmax. So what do we need to do? I need to explain a few more things before we have a proper CNN model. We need a list of parameters. Well, we've kind of got the list of parameters because every little every conv2D had that kernel, which has these little 9 numbers in. So if I vary those numbers, I'm going to get different pictures out, right? The ReLU, that doesn't need parameters. The softmax, there's the temperature, but we can just leave that for 1 for now, okay? We need some training data, because how will the model learn if it has no training data? So let's assume I've got a bunch of pictures, and I can learn that. What we also need is some means of optimizing this thing. So I know the training data, and I know the answers. Basically, I want a method of varying these parameters until the model works. So this is something which is a difficult process, but you could imagine doing this with Excel's solver function, right? There is a way of just manipulating the parameters to fix the model up, right? What you could do is just take every parameter and in turn increase it a little bit, see how it works, decrease it a little bit, see how it works, and just choose whichever's best all the time. So if you do that repeatedly, hopefully the model will get better and better, or will work better and better. And then we need to be able to test this thing. So, as I said, the list of parameters, we've seen this already, the convolution 2Ds all have this kernel. That's all we need. Training data, we're going to need lots of images and the correct classes. And we're probably going to split that into training data and test data so that we can at least see how the model's doing on stuff we know the actual answer to. Because there's no point testing it if I have to keep typing in the answer every time. It'd be better to take the training data and split a piece off. So for the optimization, rather than thinking about Microsoft Solver, which is a good model, basically we're going to take a measure of the model's loss, which is how bad the model is. And to improve the model, we're trying to make that loss as small as possible. That loss depends on every parameter. We're going to nudge all the parameters in the correct direction. Correct direction is actually going to be set by a thing about derivatives and the chain rule, but we're going to leave that for now. Hopefully, the model should improve, but it may only improve slowly because of this whole nudging process. So testing, we're going to keep some test data on one side, and then we'll hopefully see that this works. Code. So connected, yay. So I also say, this I'm installing the TF Nightly GPU version, okay? So TensorFlow Nightly is the everyday's build of the latest TensorFlow 2 story. And the problem with that is it's kind of playing with fire. So let us set up a model here. So what I'm going to do is I'm going to create a Keras model. So the Keras is this framework from which I've got these nice functions for. And I'm going to say I've got a sequential model. So it's sequentially going to do a bunch of stuff to the numbers. I'm going to have an input layer. I'm going to pass it through a bunch of convolution 2Ds. So I'm going to, instead of just producing one image out, I'm going to produce 32 different variations of the input. Then I'm going to do a ReLU. Now I'm going to do another convolutional set of convolutions. It's going to do 32 versions of those 32 versions. I'm going to do it again. I'm going to have 64 versions of the 32 versions. And at the end, I'm going to basically take this. Basically, I've chosen the sizes, so at the end of the day, I've got something which is 10 big. And for anyone who's seen this kind of thing before, 10 is the number of digits, which is kind of revealing. So I'm going to take that last flattened layer. So this is just a list, because it's flat rather than being a square image. I'm going to call that the logits, and then I'm going to take the softmax, which we saw before. Okay? And so when I actually do the model summary, so Keras being a high-level framework will allow me to do nice things like this. I can see that I've got these things, and they've got a variety of parameters. So the first kernel is basically 9 numbers, plus a bias term, which I didn't mention. And I've got 32 of them, so that gives me 320 numbers, and ditto for the other layers. So, how can this possibly do anything useful? So this is kind of the interlude. The reason this could be kind of do something interesting is that let's do it rather than a proof by mathematics, do a proof by business, okay? AI is a big hype thing at the moment, and the only reason I'm talking about it is because it works. Therefore, therefore, this must be doing something useful, otherwise people wouldn't be bothering to do it, okay? I've talked about how you would iteratively fix up the parameters, and you can kind of assume that it's going to work in some manner. So let's see whether this very simple model can do something. So with Keras, what I can do is I can then just compile this model with an optimizer and various other stuff, and then I can download what is called the MNIST dataset. Now, let's have a quick look. So this downloaded some data, fixed up some training and tests data. I can then just have a look with matplotlib and show some images. So this is what MNIST looks like. We've got lots of little, these are 28 by 28 pixel images, and these are the correct labels. So you can see that they're not perfect, but you can at least recognize them, okay? So what I can then do is I can then just do a model.fit on the training data. And here we go. So this is my GPU is now launched into doing something interesting, and it's already increased from an initial accuracy of, the initial accuracy is going to be like 10% because it's just chance, right? But now I've done 2 epochs worth of training, and I haven't got something which is 98% accurate on these digits. But that's just on the training set. You kind of expect it to be good at the training because it's seen the training. So the question is it going to do something interesting on stuff it's never seen before? Because it could just be learning the training data as if it was like a phone book, right? If I learnt the phone book, I would have no clue about someone else's number. What's key for these models is that, you know, it can learn to generalize from data it hasn't seen before. So this is what this evaluate the test set does. And fortunately, it's giving me 98.7% accuracy there as well. So this is a model which is built out of the stuff from which we learnt, which is actually interacting quite well with this model. So let's make some predictions. Oh, okay, so what's going on here? Okay, the thing which is going on here is I've asked it to give me the predictions and some test data. So give me the predictions and the test labels, which are the things. So the test labels are coming out, so this should be a 7, a 2, a 1. Okay, first one should be a 1. But it's giving me here an array of numbers. Why is that? It's because what's giving me here is a list of probabilities from the softmax thing. So this is a list of probabilities about what we've got, and so the probability that it thinks it's a 0 is 10 to the minus 11, okay? But if we go along and along, basically this 10 to the minus 1, or this is actually pretty high probability, this is almost 1. So it thinks that this is a 7, 8, 9, so this thinks it's a 7. So a nicer way to look at this is to take the argmax, and there we have what the first thing is. So yes, it's a 7, a 2, 1, This is a nasty 5, but it's getting it right. So this is even on the test set, we're doing a decent job. So on the other hand, the MNIST data set has been studied like crazy. So maybe it's all cheating, and you know it's not going to work in the real world. So let's try one more. Let's try another data set. In particular, there's a nice thing called the not MNIST data set. Okay, so this, if you can see, is basically a list of letters all in different typesets. So this is a little thing which will download it from me. Oh, hopefully this will download it from me. Download. So another nice thing about the Google Colab stuff is because it's in the cloud, things will download super quick, right? You're not using any of your own bandwidth or your own electricity, or in Singapore, any of my own air conditioning to do all of these experiments. And I don't need a fancy laptop. It will work on my phone. There's nice stuff about this. Anyway, so let's do the same kind of thing. We're going to do the training set. Oh, it's even got some corrupted files. Okay, skip them. One of the things about deep learning is it loves data. But it also means you need a lot of data. On the other hand, if you've got a lot of data, I don't care if I'm going to throw some away. So if it's corrupted, I'm not going to fix it. I'm just going to dump it. So here's some examples. So here are this is the 0th position, the A's, these are the B's, the C's. So this is what we're now going to try. Can we use the same network that we used for the MNIST and just use it on this other data set? Because, you know, why not, right? And and I'm not even going to reinitialize it. Okay, I'm going to use the same model, which is currently fitted for MNIST, and then throw it completely different data. Blimey. Pretty cool. And there we get to 93% accuracy. Okay, I'm not sure, maybe we could try some more. 95, 96, okay, there's probably more mileage. We started from a bad position in a way because it was fully trained on some other task. So let's evaluate this, cross fingers, 92, okay, maybe we're now fitting the data too much. So if we now just do some predictions, there we can see. So you can see F is right, I'm not sure, C, I. So this is wrong phi, this is a G, isn't it, right? So it's making, you can see why there are some mistakes to be made, because this is less easy than the MNIST data set. But still, we've trained from first principles something on 2 different data sets, which is kind of impressive for just a quick little thing. So let's go again. Okay, I've got some minutes left. Awesome. So the problem is, I mean, one thing you might think about is, how did I come up with the different sizes, the 32s and the 64s and the 5x5s? That seems like tricks, right? Maybe I've hidden something from you. And the answer is kinda, because this deep learning stuff started with the MNIST stuff worked in like the late 90s. But the big image stuff didn't work until started working in 2010, 2012. And people have been improving this stuff like massively. And so historically, what people have done is they've made the networks bigger, they've made them deeper, they've invented special things which they know work, and they kind of pass them around in the cafeteria. Oh, I've got these inception blocks, whatever. Or they can, out-of-the-box thinking. There's a thing called ResNets, which Microsoft came up with. So there's different ways of doing this, and it's called graduate student descent. You have a problem, and you get graduate students, and you get them to fix your problem. Okay. On the other hand, recently, because there are lots and lots of possibilities, you can choose lots of different parameters. Well, how about we just use machines to design these neural networks? So this is kind of the next step, and this has been kind of in the last year or so, people have been playing with what is called neural architecture search. So what has come up with is over time, to do this particular ImageNet problem, which you may have heard about, is a really hard classification problem, is people have invented newer and newer networks. So this ResNet, this is a fairly modern network, a fairly non-modern network, and requires over 10 billion flops to do its job, and is getting like a 78% accuracy. As you get newer and newer with this, basically there's inception, basically things of these NASNets, which are these are computer design networks, and now better. Either they require fewer flops or they're more accurate for the same number of flops. Just recently, there's been this paper called EfficientNet. This came out in May. So this is something which we do in Singapore, is we'll be reading the papers so we can talk about them at the next meetup. So we love to look at the new stuff. So unfortunately, well, I'll tell you the unfortunately here. But anyway, basically, if you're a finance person, you can see this as an efficient frontier of a trade-off. So you always want to pick the model which is higher up into this corner, because it's definitely better than anything to that side. Anyway, so you can see that gradually that the human-powered stuff has now given way to this machine-learnt structures which learn to do ImageNet. And the current winner is what's called this EfficientNet, which is that top thing to the top and left. And basically, you can see that the network it comes up with are these NBConv1s. But basically, these are varieties of the convolutional networks we did before. It's not that much different compared to some of these other structures which people come up with tons of branching or tons of genetic algorithm kind of evolved structures. This is actually a fairly plain stuff which is understandable. If you looked at the Keras output for this, it would be fairly understandable. It's quite a deep network, but it's extremely efficient. So this was published in May 2019. It's available in multiple frameworks within a few days. It was originally published as a TPU version. But the problem is that the Team Keras, which is the version of Keras which is not TensorFlow specific, doesn't understand that TensorFlow 2 is installed. So TensorFlow, I've got TensorFlow 2 installed on my VM at the moment, and I can't just click through the Team Keras one. And so TensorFlow 2 is an evolving story, which is why I had to really install it and show you from scratch. But it's gonna happen soon for different values of soon. Right? So I can't show you efficient nets right now because all the ones I tried, not working. Let's just try one last set of code, which I should never do. That one, that one, that one, that one. So what I can do is I can install my TensorFlow. It's probably already got it. Okay, so now I can import TensorFlow. Okay, so what you can see, if I look at this comprehension over models, basically, here we have in Keras applications, I've got a whole list of different models. So Google or whoever has trained, I guess Microsoft has trained the ResNets, for instance, except that now it's all kind of part of a standard process. So Google is probably creating weights for all of these networks to do what's called the ImageNet task, and I'll explain just in a moment what that is. But all of these are available as pre-trained networks, and you can load them in one line of code. So it's kind of, efficient nets isn't in that list yet, but it will be in there, you can bet, before long, right? So if I now go in here, basically I can take my Keras applications NASNet mobile, and NASNet was one of these other ones. 1 month ago, it would have been the best, right? So I can take that NASNet mobile model, is now downloading this. I guess it's only 25 megaparameters, okay? And what it's expecting as inputs is none, which is kind of the batch of images, an image which is 224 by 224 and 3 channels deep. And now I can just, come on. I'm going to import a couple of helper functions, one of which helps me pre-processes the image to make it kind of in the right format to put into the network, and then another thing to decode the predictions, which is convert the softmax output to the class label, because there's like 0 to 9 in the MNIST or the A to J or whatever for the letters. This has got 1,000 classes, so this is the thing. So I guess we're going to pick a picture. Come on, Wikipedia. There, okay. So this, as Wikipedia tells us, is a panda, okay? So we picked a panda picture. I'm now going to essentially read the file and decode that into TensorFlow. So this is all happening, unlike TensorFlow before, where I'd have to have a whole graph and a session and readers and all this stuff. Basically, it's now doing it as I type it or as I execute it. So this next cell will now just take this, it will resize it, and then essentially make it into float 32s. It'll do the pre-processing. It'll add this batch dimension on, so it's a batch of 1. So not ideal for my GPU, but in this case, I don't really care. So now I've got a tensor which is coming out, which is 1 image worth of 224 by 224 by 1, by 3. And now I'm just going to do a prediction. Plum. Come on, come on, come on. Now, okay, here we go. Oh, so it just downloaded some data. It downloaded the class names. So the classes are number N0251, okay, giant panda. So it thinks this is, with a kind of confidence or weighting of 91%, giant panda. Second guess, lesser panda, sloth bear, ice bear, and Colobus. I'm not sure what that is. Okay, so there's quite a lot of things this could be, but this is something which you can just play with quite easily. This is clearly a panda. This is ImageNet, which has been trained by Google or whatever, freely downloadable weights, which understands a whole bunch of images. Let's go back. Well, don't go back. Just give it. Last one. Okay, so it's kind of wrapping up. I've shown you the basic CNN components and building a basic CNN, and describing how it trains, and it did train. I kind of waved my hands about the training, but people are pouring money into this. It's kind of a believable argument. We trained it on 2 different data sets, and that worked. We've also downloaded an advanced pre-trained network and showed that also works. So this is success. So let me just give them in my remaining few minutes. I come up from Singapore. We have a deep learning meetup group there. Anyone who has a holiday in Singapore, very welcome to come. We meet up once a month. We've got 3,800 people in our group. Typically, we have 200 to 300 people for every meetup. Our next one is on the 6th of July, and we've probably got a bunch of people. Hopefully, we're flying people in from Thailand and Malaysia as well, because this is a special big deal. And what we try and do there is have something for beginners. So this would be the beginner talk. Something for the bleeding edge. So if there's the efficientness paper, I would talk exactly how they did this. And then we'd have some lightning talks, just like here. We also run deep learning courses in Singapore. The next one is on July 4th, 5th. But we also have other advanced modules like computer vision with all sorts of different funky vision things, like self-driving cars, facial recognition, advanced NLP, which is to use not only time series or LSTM kind of models, but also going into the newer transformer models like BERT and GPT-2. We also have a self-supervised thing. So we've got a bunch of courses. And in Singapore's really good in that the government wants Singaporeans to know stuff. So they will fund Singaporeans money. So this is a key part of the business model. Good for Singapore, doesn't work here. So what we're interested in doing next is also exploring doing courses here. So, but we also kind of need to understand who is interested in this stuff. There is a bit.ly link, which if you're interested in any way, or even if you tell us, please don't come, we'd be glad to hear that, because that's all good data, okay? So Thai_courses.